Okay. So I think it's a good time to start. So this talk is about successful and not yet successful optimization in Valgrind. So the first question you might ask is, how do we classify the successful and the not successful? A colleague at my work has said the successful is what I'm writing and the not successful are the one that the others are writing. And no, in this case it is not that classification that I will use, because I will speak about two optimizations that I did and one which has been committed in the SVN repository and the other one not committed yet. So the content, I will speak about two optimizations, the generalization and optimization of the massive execution tree concept. So I don't know how many here were there at the talk of this morning, where I've described the functionality of the X tree, and here we will speak more about its internal implementation, and as we have seen this morning, this has been committed. And then I will speak about another optimization, which is optimize the stack trace recording, which is done in Valgrind, and this is not committed yet, and we will examine why. So massive execution tree, quick reminder, it maintains a heap profile, and this heap profile associates the allocation stack trace with the allocated memory size. And so for each allocation, what does massive do? So it has to get the stack trace and it has to insert it in X3 if this stack trace is not yet present, and then it has to add the newly allocated size to the stack trace memory size. And after, because it has to be able to, when we do a free operation, retrieve this stack trace in order to decrease the memory used by this stack trace, it is adding the allocated block and the pointer to the stack trace stored in X3 in an hash table. So malloc, we do this, and this as part of malloc is done so that when we do the free operation, we can retrieve the stack trace that allocated the memory, so that we can decrease the currently allocated bytes by the stack trace. And so for each day allocation size, using this hash table, we subtract the allocated size that has just been released from the stack trace memory size. So this explains basically the massive algorithm using the current way it is done. So here I will explain more in detail how it works on this example, where we have function main, which is calling x, a, o, and then x again, and then you see x is calling y is calling a malloc. By the way, you see it will be lost, but that's not the point. And similar call from a calling b calling malloc, and then you have function o directly calling malloc. So with such a call, we will end up with such an X3 in Valgrind 3.12. So the way the tree is represented in 3.12 is quite classical. It is just you have a top node, and then you have children, and from malloc, if we see, for example, that main, the stack trace main calling A, calling B, that is called malloc, this will be stored in the tree with pointer in this direction. Now we also have to store pointer in the other direction, because when we add the stack trace in the tree, we will add it like this. But when we will release, when we will free the block which has been allocated by the stack trace, we have in fact to start from here in order to decrease the size of all the blocks which are, of all the functions which are in the call stack. So this is a classical tree representation with pointers to children, but we need back pointers. So in Valgrind 3.12, we also have back pointer in the tree in order to go up and down in the tree. So the data structure, again in 3.12, which stores this, is represented, is shown here on the screen. So we have the code address of such a block, so of a certain call in the stack trace. So for example, this might be function A, or might be function B, or might be main, is a program counter inside main, or inside function A, or inside function B. Then here we record for so this in 3.12 terminology, this is an execution point, so one of these small square rectangle that I present, and we store here the size of this block, and for the bottom execution point, so the lowest level in the tree, it is the size for this precise stack trace. And so after, if I go back to the previous thing, so here, these are bottoms execution point, and we see here a non-bottom execution point. The size here will be the sum of the things which are pointing back at this execution point. And so after, we also need the children, an array of a pointer to an array of pointer to children, and because each time we are adding a new stack trace, we might have to expand the number of children. Here we have an array which is bigger than needed, and so it's expanded from time to time. So this is the real number of children, and that's the max number of children we can add, because, for example, the size of this is doubled each time we reach something too small. So that's the data structure in 3.12. So massive snapshots, how are they implemented in 3.12 based on this thing? So the massive snapshots, they record the evolution of the allocated memory. You have the summary snapshot, total memory size, the detailed snapshot. In 3.12, a detailed snapshot is a trimmed down copy of the massive X3. So this data structure with pointers and so on, when massive 3.12 takes a snapshot, it is cutting bits and pieces of this tree. Effectively, what massive is doing is that the non-significant stack traces are aggregated. So if you use massive, you know that it will show you by default the stack traces which are significant with full details, but when a stack trace is allocated less than a certain percentage of the memory, it will regroup all that in what is called a non-significant stack trace. And when massive takes a snapshot, it will copy the X3 and then group together the things which are not significant in order to reduce the size of the snapshot. So the non-significant stack traces are aggregated in 3.12. And so we have, in fact, when we take a snapshot, we have a parallel data structure which is used to store the snapshot. So we had execution point, and here we have snapshot execution point, which basically has things that we recognize. We have the number of children and a pointer to an array of pointer to children. Here we don't need anymore this max number of children because this is a snapshot and it will not grow anymore, it will not change anymore, so we don't need to oversize this to avoid permanent reallocation like in the real original snapshot. And then we have here something which is for the non-significant part of the snapshot execution point, which records the things which are insignificant. So in 3.12, we are using a classical tree representation with bidirectional pointer, and then we have a kind of parallel structure which is derived from the full X3 snapshot. So the massive output MS print you recognize here, and the production, you see the structure of this matches the data structure that we have seen. Like, for example, we have here 0.25% in one place which are below massive threshold. And basically this structure is just produced from the snapshot X3 data structure that I explained the slide just before. So now this I have quickly described how it worked in 3.12, and now I will describe what were the objectives for the new implementation. So of course the first objective was to still support massive heap profiling. It would be a little bit sad that the new stuff would not support massive. So the other thing is I also wanted to have heap profiling reporting supported by other tools. So this is, I wanted to generalize the memory reporting. And a sub-objective of allowing other tools to produce memory report was that if we don't use the new feature in memcheck, for example, or Valgrind, I want to have no impact, no CPU impact or ultra minimal impact on tools. So if you don't use the new X3 functionality with memcheck is not impacted. So we want to have it also generalized. So we want to have this new functionality usable for more data than only the allocated memory, like what we have seen this morning. We can use it for the number of blocks, for the total freed blocks and so on. So it's more, when we look at memory reports, it records more. It can record more than just the allocated bytes, but also for totally other types of data, like for example the leak. We can use the same data structure to record, to represent leak information or system call information, like we have seen in the experimental syscall this morning. So an objective was to generalize the data structure so that it could record something else than a size, massive execution point only records a size, and the new implementation here can record variable things. So that's example of what can be stored. Also, I want to have more output format. So the massive 3.12 only produce the execution tree in massive output file, and one objective was to output the same kind of data, but in a K-cache green call green format. Because as we have seen this morning, using K-cache green to visualize a big amount of information, like a lot of stack traces or various events, this is quite handy, quite economic to use. So all this has led to implementing the X3 concept as a new module, tool X3.h, which is of course usable by Massive, but it is now also usable by other tools. So in 3.12, the execution point data structure that we saw was specialized for Massive and was part of Massive. And the new tool X3 is part of Valgrind core and can be used by other tools and for other objectives. Finally, I also want to reduce the memory usage for the data structure, because if we want to use it for more things in memcheck tools and green tools, or for example for syscalls and record more data, it's nice to be able to have less memory use by this data structure. And final objective is that we should use less memory, should use less CPU, and that's always nice objective that we can use both aspects. So how did we look at this? How did I try to achieve this objective? So the first observation is that many tools, namely memcheck and green, they already record a stack trace for each allocation. And this stack trace is recorded as an exe context. An exe context, it is a stack trace, but this stack trace is stored in a hash table, and it has an EQ, exe context unique ID, which is an integer multiple of 4. So an exe context, once we create one, it is stored in a dictionary of exe context, this hash table, and never disappears. So it's a dictionary, while during run, we always add exe context to the exe context dictionary, we never remove it. So they are added to the hash table, never removed. And so the idea is that tool X3 will reuse the exe context to sort the X3 stack traces. This is what allows memcheck and Valgrind to use X3 without incurring additional costs during, let's say, normal operation, because the exe contexts are there, they are created in any case, and so can be used for other things. Some other observation about application behavior, which is helping to produce an optimized version. Most applications are doing a lot of calls to malloc and free, and most applications exit only once. I don't mean that we have some application that exists twice. What I mean is that some applications do not exist. So most applications exist once. So massive reports, the reporting, and more generally all X3-based reports that we want to do, they are all put at termination time. And so what is nice if you want to reduce the CPU usage is to decrease the CPU that we spend when we do malloc-free, and push this CPU as much as possible to the reporting side. At the time we do the report, so termination or when we do the report. So pub_tool_x3.h minimize the work for malloc-free, or more generally, minimize the work which is done when you are recording an event during the run. So first, one thing to optimize the CPU is it only maintains the data for the leaf X3 nodes. Massive 3.12, each time it was adding it was allocating a block, it was increasing the size in the leaf execution point, and then was always propagating that up to the tree. And the new implementation doesn't do that, it only stores associated to the exec context the data which is being recorded. So for example, it increases the number of allocated bytes for each malloc. So the additions that we have to do in order to represent in order to do the massive report of the K-card grid report, which is main has allocated 20 megabytes, because it has called F1 that has allocated 15 megabytes and F2 that has allocated 5 megabytes. The additions who say that main has allocated 20 megabytes, we don't do that when we do malloc-free, we do that when we produce reports. So how is the data structure looking like in 3.13 SDM? So the basic idea is we have an array of data. So the first difference compared to the execution point that we have seen with massive 3.12 is that the data is a simple, so when we store the data, it's a simple array, which is here is a number of allocated bytes, here is a number of allocated bytes, here is a number of allocated bytes. And this is associated with exec context using two other arrays. So you remember an exec context has an EQ, a unique identifier, which is an integer multiple of 4. So here we have here an array which is storing pointers to exec context. And how do we know when we have an exec context where it's stored? We have here another array which is used as a table to retrieve the offset in this array and in this array where the data is stored. So imagine, for example, that we have various exec context, and so we have maybe an exec context which has an EQ which is 8. So 8 is the unique identifier of an exec context. We divide this by 4, and then we obtain 2, and this 2 is we record the offset in this array and this array where we store the pointer to the exec context and the data. So this array divided by 4 EQ to XEQ. So XEQ is a new unique exec context identifier, which is in fact the offset in this X3 data structure. So the typical word for an allocation using this data structure is to get a stack trace and search its exec context in the hash table, and this is part of a standard module of Valgrind core. And so a small note is mencheck and Valgrind. They already have the exec context, so it's not need to do a new stack trace, because in any case, mencheck and Valgrind are already recording a stack trace for each allocation and binaries also. So for mencheck and Valgrind, there is no additional unwind which is needed. Then we obtain the new XEQ, so the offset in this data structure, by indexing in this array the EQ of the exec context divided by 4. And then after, when we have retrieved this the offset in these arrays, we can just add the data that has just been allocated to this part. Of course, these arrays, they start with a small size, and then they are expanded if needed. So if we have new exec contexts which have an EQ bigger than this, we will reallocate this array, and similarly, these arrays will also be allocated. So you can see, in fact, that this is a sparse array, because not all entries are used, only the exact context which are really used by an X3 will have an entry here. This avoids that these arrays are sparse because these would contain a lot more data. This is bigger, so this is a simple integer, that's a pointer and two integers, and this is variable size data, which depends on the reason for which you are using the X3. If it is memory, you can have 5, 6 data like we have seen this morning, the number of bytes, blocks, and so on. And if it is syspoles, if we would enrich the syspole X3, it might be a lot more data depending on this. So it's relative. So then, based on this, how do we implement snapshots? We implement snapshots, but it's very easy. In fact, the only thing we need to copy is to copy the data array. Because all the rest, the array of exec context and this array, they can be shared between snapshots. And so that's a big change compared to what Massif had. Massif had two data structures, one data structure for, let's say, the live execution tree, which was full and contained all the stack traces, and then it was copying the complete structure, truncating some bit and pieces in order to reduce the memory used by the snapshot to the relevant part. And that was needed to effectively not use too much memory. But here, because the only thing we have to save is the data, in fact, a detailed snapshot, we don't have to truncate the let's say, not significant part, we can just copy the data. So this snapshot and the X3, the active X3 can be output in Massif and Valgrind or Valgrind format as I explained. So the output Valgrind Valgrind format is very simple. We scan the exec context in the X3, we output each caller call pair, we output the data image for the last pair and speech. So to output the Valgrind format is really easy. Now to output the Massif, to be able to output a Massif format was slightly more complex. So this is the algorithm which is used to output an X3 in a Massif level. So the first thing is that we have to store the X3 exec context by their array of program code. So what we want is to, if you see, for example, at depth 0, we want to group together, we want to store and have together all the exec context which have the same program counter at depth 0. And then inside the exec context which have the same program counter at depth 0, at depth 1, we will also at depth 1 sort them by the same program counter. So in other words, we have at level 0 things sorted from program counter, and then at level 1, in the subgroup which has the same program counter, we will there also again store by program counter. So this sorting is CPU costly, but in fact this is also not really dependent on a snapshot because the order of the exec context will always stay the same if it is for one snapshot or another snapshot. So this is computed once when we need it, and then it is kept there and maybe updated if new exec context were done. Then after, when we have sorted this, when we have built this sorted array, then we output the exec context group recursively. So we define the sorted exec context at depth D in subgroups which have the same IP, as I explained, and which have the same parent. And then for each group, we add the value of its exec context. By the way, here is the place where we are doing the additions. So we only do the additions up in the tree, if you want, when we produce a report. So if you call malloc-free, 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 Massif 3.12 was add, subtract, and here with the new implementation, we just do add, subtract at one single place rather than to go completely up in the tree. So this is one thing which makes this CPU more, better for CPU. So when we have for each group, when we have added the value of all the exec context member of this group, we sort the group by total size because the Massif output is sorted. The bigger group at the beginning and the group having allocated less after. And so for each group sorted by total size, we output the function, the total, and then we recurse we output the exact context of the group, and at one at the depth n plus 1. So I managed to put the algorithm on one slide, but if you look at the code, it doesn't fit on one page. It's so some stats measurements based on this. So first, what is the size of the new X3 module? So this has added about 1,400 lines of C code, and so source comments and so on included, and slightly more than 400 lines of .h, which describes the interface to the new X3 module. Massive, the size of massive code has decreased, 500 lines less. And now what is interesting is to see how much code we have to write in order to have a tool using the new module. And an example, Valgrind, in order to have Valgrind be able to produce a memory report and also respond to VGDB command to output an X3, it's 42 lines of code. So you see, by doing a module here, which is more code than we had before, we have it usable by other tools with a very small amount of additional code, and we have, of course, additional functionality because it is more general, all can be output into form. So now some real-life performance measurements. So this has not been measured on this laptop, but on a very fast machine, so 4 GHz core. And I did this measurement with an ADA application, which I'm using for my work. So it's a graphical map application, which is starting up, loads a lot of data, and then with this thing, I did a refresh, and then it exits. So it's doing 2.5 million of malloc and 500,000 free. And we have in total, in this application, 85,000 different allocations stack trace, 35,000 different free stack trace, an average stack trace size of 24 frames. And so this is to show a nice picture. So this is the application which has started, and we just showed some more. And if we would show all the objects that have been loaded, then it would so this is all the objects which are loaded and then put on the map. Of course, our operators are usually not showing that amount of objects, but it was just to show that this was doing a lot of. These are all the aerodromes, the waypoints, the navigation points, the routes and so on used by the flights, the airspaces, the control airspaces. So it's the whole structure of the let's say the air traffic. So, what is the performance impact of the X3? So, massive tool 3.12, how did the change when we went to 3.30? So first, the massive needs to have its own data structure, and now the X3 has its own data structure. So in total, for this application, we went from 327 megabytes of Valgrind memory to 151 megabytes. And CPU, this application was running in 28 seconds and now runs in 13 seconds. So you can, I explained that this morning, that you can also, thanks to this, produce X3 memory report for and check. Allox just gives the currently allocated memory. So what is the overhead of using X3 memory equal Allox? Well, easy, during run, if you do this, no impact. There is no additional impact, zero impact. And of course, if after we have to produce when we have the X3 file, so if for this application, it's a file of 40 megabytes and it's produced in about 0.5 seconds. Fast machine access. Now, if we do then check X3 memory equal full, which does more work because it has to, while it runs, records a little bit more information. So this has an impact during run. So it's a neglectable impact during run because I explained the exact context is already captured. And the only thing which has to be done is a few indexing in this array and then do some additions. So it was even very difficult to measure what was the real impact because the variation between runs was higher than what I was. So it's maybe 1%, 2%. The history file for the memory equal full is bigger because we have more events. It's 120 megabytes produced in about 0.8 seconds. Note that the massive file will be a lot bigger because massive file format does not have any compression features that the code reader has. So conclusion about history. The history module is easy to use for different data. You can use it for memory report, leak reports, and I hope this code one of these days. And then we have more tools that can produce image files. Massive is faster, use less memory, and so this is a successful optimization, and it was complete. Okay, now let's switch to the other optimization. It's not committed, and that's Valgrind history level equal full. So this parameter to Valgrind tells Valgrind to report two stack traces for a race condition. It reports the current conflicting access and the previous access. And this is an example. This is the current access, and that's easy to obtain because Valgrind just detects a race condition, so it just unwinds and has this stack trace. But it has to tell the stack trace, when we do this, of the previous stack trace which has accessed this memory. But of course, we can have a lot of these stack traces. If you have 10 traces which are paying, maybe a lot of them have accessed a lot of memory, and so we have to record a lot of stack traces to report this record. And the idea was to optimize this. So, as I have explained, history level equal full implies to record and store a stack trace for many read or write instructions. I say many, not all, because there are some optimization in Valgrind for repeated reads in the same thread segments. Basically, Valgrind has to see the coordination between threads, and we can say between two coordination we call this a segment, and as long as you are inside the same segment, we might optimize the recording and not necessarily record all the stack trace for all access to memory. So the Valgrind stack trace unwinding is very optimized, but it's still costly. Julian has done some measurement, I think, 1 to 2 years ago, to evaluate the cost of the unwind on the x86-64 bit, and to unwind one level of a stack trace. So, for example, you have main point A, B, C, to see that, to detect that C was called by B. This is unwinding one frame, and this costs about 220 instructions. So remember that we might have to record a stack trace for a lot of reads and a lot of writes. So it means that if you want to record a stack trace for one read, you have one instruction, and then you might, if you record 8 frames, you might have to execute something like 2,000 instructions, but only to do the unwind, because after you still have to store it somewhere. So you see, Valgrind it's really a heavy activity, and it's storing a lot of these stack traces. So, what is the cost of this history level equal full? So if we, again, I've used my graphical application, which is a multi-threaded application, by the way. With history level equal done, it runs in 46 seconds. With approx, which just records the segment start and segment end of the race function. It's almost the same cost because that's only when we have thread synchronization that a stack trace has to be recorded. And when we use history level equal full, we have about 73 seconds, so significantly more. With this application, we have about 120 million stack traces of 8 frames that had to be computed, and the measurement I did was 20 seconds of this additional time is used to compute the stack trace, the unwinding, and 7 seconds is needed by the overhead of storing them somewhere in a specialized data structure. So we see that a lot of the cost of the history equal full is the unwinding, and a part of the cost is the storage. So, recorded stack trace, let's take, for example, the program for which I have shown the race condition. We have here x++, and it's an unprotected modification relative to the parent thread. And so the question is, how many recorded stack trace for this child function? So we have one access. Do you have an idea how many stack traces are recorded by Valgrind for this? I see that Julian is thinking.
I don't know the answer, but I'm sure the answer is too many.
Not really, but you might imagine there is one access, and so there will be one stack trace. No, not really. Here is the code, and then I have explained where we have a stack trace which is recorded. So this function is called, and when we are calling this function, we have to write the return address to the stack, and this is a write operation, and if it is a write operation, we are recording a stack trace.
Right?
Yes, I think so.
Okay, my understanding is different, but
I think this is correct. Then we push the FBP, so we write on the stack, and there is no recording for this one, because as I explained, we have some optimization, and then we try to see that we have done two writes at the same place in the same segment, so there are a bunch of optimization which I do not understand, and so this one, we have a write, but we have no record. So here, this is just moving registers, no memory access, no stack trace. Here we have a write on the stack, again, no recording optimized. Here, again, we are recording the read to bits, then we add one to the register, then we write, and we recording the write to bits, and then after we return, and here we have no recording because it's optimized, but here we are again, when we do the read from the stack, and we again record the read from the stack. So if you see for such a simple function, which is a few instructions, you can imagine you have to do X recording times 8 real y times 220 instructions. So you can imagine why, no, you can understand why a green runs somewhat slower than a big runs. So observation about stack trace, many instructions, most instructions, in fact, we only change the top instruction pointer. So that's a nice observation to see, and that is the basic idea with which I have optimized the stack trace recording. So the optimization idea is to cache the last computed stack trace, and so if the cache stack trace is valid, then the new stack trace is the cache stack trace, and we just replace the last instruction pointer of the stack trace by the current instruction pointer. Now, of course, that's easy, but we have to invalidate the cache stack trace sometime. So the cache stack trace is invalidated by any instruction that changes the control flow. For example, call, return, etc. So where do we store the cache stack trace validity? The cache stack trace validity is stored in a shadow register, because then Green does not use them, I could use them, and I decide to use the stack pointer shadow register. So if it is 0, it means the cache stack is invalid, and 1, the cache stack is valid. So it is set to 1 when the runtime of Green computes a stack trace, and then at instrumentation, when we instrument the code, easier to tell it like that, then the instrumentation adds assignment of 0 to the shadow stack pointer for any intermediate representation exit kind, which is different of boring. Boring means just go to the next instruction. Anything else is a kind of jump, and a kind of jump means that we can't just replace the last instruction pointer, so we invalidate the cache stack. So that's a basic idea, very easy to understand. Has everybody understood? Yes, so it wasn't easy to understand, right? So what is the cache stack trace bit rate for my application? So we are computing about 20 billion fresh stack trace, and then we have used the cache stack trace with exactly the same IP, so it was a loop, in 19 million stack trace, and then we have 78 million stack trace where we have used the cache stack trace and replaced the last IP. The CPU time has decreased from 7.26 seconds to 58.8 seconds, so that's a really nice improvement. And so it's a nice improvement. It's an idea that looks simple, all regression tests are okay, and so why is this not committed? I should have finished the talk, then I would not have to see why, to say why it's not committed. But I still have 15 minutes, so we'll be obliged to say why it is not committed. Well, first question is, how is this patch tested? Well, it's tested with the regression test. And with the self-test that I have added, the self-test says for each stack trace, we compare a brand new, freshly computed stack trace with the stack trace that I compute with this updated cache stack trace. And if they are the same, I'm happy, and if they are not the same, then there is probably a bug in what I have done. And so the regression test and the self-test have revealed corner cases which have complexified the idea. So first, the unwind errors are not self-repairing anymore. What does that mean? So the unwind algorithm is not always perfect. For example, it can give wrong result in some case like function prolog. In 3.12, and still in 3.13 because I did not commit this, a wrong stack trace is only shown to the user for a race condition in the prolog. But with this idea of caching, with the optimization idea, such a wrong stack trace can be used for the full function. If the full function is just a bunch of instructions like that, the wrong stack trace computed in the prolog will be used for the rest of the function, and that's not good. And so, a consequence of this is that we need to have more correct unwinding at each instruction. By the way, when I tested dispatch, I discovered some bugs in the unwinding or some limitation, and I did one or two improvements in the unwinding algorithm. So back to dispatch, we have improved the unwind. Another thing which is very special for Valgrind is that we do unwind inside an instruction. That's really bizarre. What does that mean? So let's see intermediate representation before optimization. So we have here the push instruction, and we see how this is translated. So we take the base pointer we assign to T0, we compute the stack pointer minus 8 we assign to T1, we assign the new value to the stack pointer, and then we store T0 in REP, and then we go to the next instruction. So this is before instrumentation. After instrumentation, each write might have additional calls to help us which have to do an unwind. So this thing we have to unwind, compute a fresh stack trace maybe if it was not invalidated. And here we are in fact in the middle of an instruction. We have already changed the stack pointer, but the instruction pointer, the program pointer is still the thing. So we have unwind information in the debug info, but the unwind information describes what to do here or what to do there. It doesn't describe what to do in the middle of something being done, and that is somewhat annoying. Again, not really impacting 3.12, because this kind of thing push unlikely to have a race condition there, but if we reuse this stack trace for the rest of the function just using the last IP, it might be conformed. So to see, I have added a feature which is, I have added properties to instruction, which indicates to fix up the stack pointer. The idea is to mark the push-like instruction with a fix-up property, and then the generated helper calls, when it sees I'm on an instruction which has this fix-up property, will automatically fix the stack pointer so as to redo the addition, which compensate for the fact to be in the middle of the instruction. So here, when at the instrumentation time, when this has been marked as fix-up SP, then the generated code here we call the same kind of helper, but indicating that the fix-up has to be done. So invalidate cache stack trace, another problem. Reminder of the simple invalidate ID, instrumentation as puts cache stack valid at the end of the block for everything different of boring. Well, the small problem is that some call instructions do not give an exit instruction because some calls are somewhat inlined by the Valgrind machine. So for this, again, the idea is to mark the instruction with a call property, and then again at instrumentation time, if we have a call property, we will add an invalidation. So this is an example where we have two properties added to the instruction, a call property and a fix-up property, because this call queue suffers from the two problems I have described. And so we are here calling the fix-up, and we have added here an invalidate of the cache stack trace. Self-test subtlety. Sometimes the self-test detects a difference between the version 1 and the updated from cache stack result. So the self-test says, here there is a bug, because Valgrind 3.12 would compute this, and the cache stuff computes that. Well, sometimes the unwind is incorrect, because what I have discovered here that, for example, missing fix-up in the middle of instruction, Valgrind 3.12 also suffers from that. So compute the wrong stack trace, and for all the instruction when we have a fix-up, in fact the stack trace computed by Valgrind was wrong, but it was not a big problem because it was increased. So the cache stack logic in this case produces a correct result, and now in the self-test I've added some logic to detect the case where the new implementation is better than the previous implementation. So now I have run the regression test and self-test, and I think, to my knowledge, that on x86 and x86 64-bit, I think this is all okay, and the self-test detects that all is okay, except the known case where it is better than the previous implementation. But the state of other platform is completely unknown. So should I commit this Valgrind optimization? Not too sure, because we need to somewhat change a little bit of text to have these properties, and it's untested on some other platforms. So maybe I could commit with a command line option to enable, disable this optimization. Need to see if before commit we should not validate on other platforms, and maybe we have to change a lot the approach, because maybe the property concept that I have added maybe could be useful to help Valgrind on difficult platforms. Again, I don't know everything in this area, but I understood that on Power PC and ARM, Valgrind has some difficulties. And maybe using this kind of property might help Valgrind, and then we should do something more general. And so maybe we need a tool-independent module, tool efficiently track call stack changes.h, maybe another name, usable by Valgrind, Valgrind, and so on, rather than this rather specialized Valgrind optimization. So conclusion, nice optimization can often be derived from very simple observation, both for the massive stuff and for the Valgrind. Some optimization, however, are not that simple, like we've seen with Valgrind. So is it okay to add this complexity? Well, for massive was really clear, yes, because it was additional complexity, but usable by all tools, and so it's a benefit. But so if we have additional complexity in tool reusable module, it's relatively clear that it's good to commit. But we have, when we have various bits of logics which are involved in the Valgrind and so on, to do more or less the same, it is not that clear to me that this is nice to commit, at least not without discussing it a little bit more in depth. So Valgrind, as we have explained, has some complex logic to maintain a stack trace. Valgrind would have a different partial logic to maintain a stack trace, and that's very good. Voila, so this time. Some questions?
Would it be possible to expand the concept of having an unbound stack trace, but have, like, so if you return from a function, most of your stack trace that you had in the function is still valid, right?
Yes.
So why wouldn't you keep that around for future stack trace?
Yes, it's an idea to look at. In fact, as far as I understand, that's, I think, what Valgrind tries to do. It tries to understand what's happening to the stack trace and maintain it on a permanent basis. But I don't know too much the problems that Valgrind has. Maybe Julian knows more about the difficulties, but on some platforms at least it's difficult. Maybe on the x86 platforms we could do this relatively easy. No, I'm not sure. But yes, it's one of the possible ideas. Another idea is because these 8 stack traces are often the same except the last one. Another idea I had was to, in fact, store only once the common thing and only have a pointer to the 8 stack trace, and an additional telling replace the last one, so it would decrease the memory. So yes, this type of approach might open the door to other optimization, but the question is, should we invest more in this approach, or should we invest on this nice new module here that we should maybe develop? But yes, what you suggest is clearly some possibilities. Any other question? You still have 5 minutes at least. is there? Huh? Well, usually, no, there is no plan, but it's about 1 per year usually, so I guess around September is the most probable what will happen. But Valgrind is very easy to compile. It doesn't have a lot of dependencies, so you just need the autoconf tools, the compiler, SVN to check out, and then you can compile your own Valgrind. It's really very easy. It's not like if you try to compile GNOME or LibreOffice or whatever you might need to download plenty of things. If you want to experiment with an SVN version of your Valgrind, it's really trivial. If you encounter difficulties, send you have Valgrind discussions on IRC, so you are welcome to try the new version before this. And usually it was, for example, at my work, and I'm working with plates. So if it crashes, it might be annoying. At my work, we routinely use the recent Valgrind of SVN for really big applications. So yes, the SVN version is usually working for us. Other questions? No? Thank you.